afternoon. Good day to you. We are going to be talking about active galaxies tonight. We are back. We are here. We are with you. Welcome to the live. Welcome to one. Welcome to all. So very nice to see you. If you're joining here on the live stream, and also if you're seeing this as a video upload later on under the live tab, welcome as well. Reese, hello. The mod is here first. Hello, Reese. How is everything? How's everything going tonight? We are here. We are live. Good morning. Good morning to Belgium. Good morning to the UK. Good morning to Europe. Good morning to Germany, Poland, Ukraine, France, Sweden, Finland. Good morning. Good morning from North America. And we have been covering a number of topics related to astronomy lately. Good, thank you. Literally woke up about 10 seconds ago. Well, in 10 seconds, the live has started. Yes. Good morning. Good job to everybody who is waking up today. Hope you have a great day and an amazing rest of the week into the weekend and a next week and a next week and all of the weeks I hope go really well. I'm wearing a turtleneck shirt today. I did not swim today, which means that I am not quite doing my exact routine like normal. But here we are. I have this book. I have my Foundations of Astrophysics book, and by Barbara Ryden, Bradley M. Peterson, the usual. We have been on a good run talking about astronomy lately. We covered planets, we covered the moons of the planets, we covered the Jovian planets, we covered all of the variety of things in the solar system, and also learned that exoplanets have some difficulties in observation. Something's on my screen, so I have a weird mark there. And we noted the extremely startling types of exoplanet results that we have been receiving from doing the work so far on that topic of finding exoplanets. So from there, we actually moved on to galaxies, and we talked about our galaxy, the Milky Way galaxy. We also talked about galaxy classification and looked at spiral, elliptical, and irregular galaxies. And today, after I share the live here on my channel, we will talk about active galaxies. Yay! Active galaxies. So, how is everybody doing? If you want to put something in the chat, I will read out your comment, especially if it is a good one that can be read. And also, I will give you a shout out. Hi, Cytonic Space. Hi, Tessa. How are you? So, let's see. Yay! There we go. Hi, Ray Phoenix. Tessa says, good, how are you? Thank you. I'm good too. Thank you. Nice to meet you. Ray Phoenix says, hi, hello. Are you going to school? School says ever. Butterfly joined says, hi, hello. Rich knows, go to sleep. You look tired. Okay. Isaac says, Tessa is annoying. I don't know. I think I like Tessa so far. Sparkle Place says, IH. Hello, Isaac. Hello, Sparkle. Hello. Robert Anaya says, what's up from California? Yay, welcome to Californians. Welcome to the live. What do you do on this stream, says Nameless. We talk about astronomy, physics, and cosmology. We will be talking about Active Galaxies today. Hello, Butterfly joined. Hello, Ever. Ever says my mom is cooking me in the oven. Okay. Ronnie says, okay. Scadzilla says, hello. Wow, Reese, the mod is very active today. So if you want to stay in the chat and participate, you might want to tone down on the weirdnesses. But otherwise, welcome one, welcome all, and thank you so much for being here. Hello. Can you please like the live? Thank you for being here. Please do like the live. I'm going to share the live real quick. Scottzilla says, watching from Dallas, Texas. Welcome to Texas. MC24 says, I saw on TV that planets eat each other. Eat each other. Well, sometimes there are collisions with planetoids as part of planet formation. We might have had a collision with the planetoid, is what we think how our moon might have been made actually, as an ejecta in that process. So that is, it could very well be sort of, it's not quite eating each other, but it's collisions with planetesimals, which include asteroids, comets, and other planetoids, and then sort of contributing further to that particular planet, or sort of exchanging some kind of angular momentum, or having some kind of ejecta come out and be the moon of that planet. Those are all actually things that are well within the realm of planetology. Nolan says, what is 1 + 1? Hello, Nolan. Hello, CJ. What's your opinion on Pluto? Well, Pluto is classified as a dwarf planet now, and I'm quite all right with that, for several different reasons. You know, it's a dwarf planet, it's okay. Butterfly Join says, bye. Bye, Butterfly. Hi, everybody else. Diesel71 says, hi, how are you? I'm good, how are you, Diesel? I subbed, thank you. Where do you work? Andrew, you said you were gonna get food, but you're here on YouTube. You said we were gonna get food? Oh my gosh. Okay. Robert Anaya says, how do we know the universe is expanding and what is causing it to accelerate? Is it true we found water on Mars? Yes. So the universe is expanding. We have certain redshift data from supernovae, actually. So certain objects or certain transient events, in this case, supernovae are ultimately transient events, but in astronomy, there is a certain thing called standard candles. So those are used to basically compare the magnitude of luminosity width in order to kind of put a baseline down and be able to compare in a way that makes it basically fair. So we actually have certain supernova data that we use, and it's a lot of different supernovae, and those events happened at different redshifts. And looking at certain specific ones which have the same absolute magnitude but different apparent magnitudes of luminosity, that's how we knew that the universe is expanding. So the reason for this luminosity difference is the expansion of the universe, and not the fact that, you know, they should have that difference basically in any other way. And then so we can also go through this in a bit more formal manner. I just wanted to answer the question quickly, and then I can actually cover that portion about the expansion of the universe in just a little bit here. I know I talked about talking about active galaxies, but this is a very good question, the expansion of the universe. So we can touch upon it from a cosmology point of view, of course, which this is. So we know about the expansion of the universe from this type of redshift data, and it was a very well studied thing. It was a big deal, and then basically this is the confirmation for what we call dark energy. We don't really understand exactly what it is. It's a topic of research, but that's why it's expanding. It's attributed to this dark energy. Yes, thank you everybody for being here, which is causing this type of expansion. And also, we talked about the cosmic inventory, which is all the different types of ingredients in the universe. And we talked about, photons being one, neutrinos being one type of ingredient, baryons being an ingredient, dark matter being an ingredient, and dark energy being an ingredient. So if you kind of follow the lives where we talked about the evolution of the universe from the Big Bang to its current state, where it's dark energy dominated, it might make a bit more sense. It might bring more perspective to this exact topic that you ask about. So the expansion of the universe is because of dark energy. And what dark energy exactly is the number one question of the universe. Number two being what dark matter is. So dark energy, what it is an open question that we're all welcome to research. And what is dark matter is the second biggest open question, which is also something we welcome everybody to research. So what you ask is an extremely pertinent question. The expansion of the universe is attributed to dark energy. So sometimes people think of dark energy and dark matter as sort of similar things, but they're not. Dark energy is definitely a large scale cosmological kind of phenomena and topic. So if you wanted to study dark energy, it's like saying that I want to study the expansion of the universe and understand the universe from a cosmological point of view. Whereas dark matter has to do with extra matter, invisible matter, dark matter. These are all sort of synonyms of dark matter, as well as matter that just doesn't interact with photons or with radiation, with electromagnetism, but it does interact with gravitation. So we found evidence of dark matter even within our own galaxy. So that topic, the dark matter topic, as opposed to dark energy, is something that you can study even in the realms of our own galaxy. So it can be a galactic study or just like an astronomy study. So astronomy is more specific. It doesn't have to include the whole universe. It can include something like just our solar system, or in the case of dark matter, it should probably include our galaxy because it's more of a galactic kind of thing. And also the fact that dark matter is one of the cosmic ingredients that comes from a cosmological point of view. So I'm trying to say that dark matter is more of a cosmology as well as an astronomy, astrophysics topic. So in all of these fields, you could study it. Whereas dark energy is more of a universe kind of topic. It's the expansion of the universe that does not come up unless you're looking at a much more larger scale and really go to a different redshift type of distance away. And then dark energy is very important because it turns out that in the universe, actually 70% of the critical density of the universe, as in what the universe is made of, right? Like we are a small part of the universe. So we now have to really zoom out. Like people think, oxygen, nitrogen, earth, what we're made of, we're mainly made of baryons in cosmology. We're grouped under baryons. Baryons are protons and neutrons of just like, the regular elements, in other words, right? We're made of just normal stuff, regular elements out of the periodic table. And those fall under baryons, which in the overall picture is only 5% of the cosmic ingredients at this current time. So it used to be that the universe was very radiation dominated in the beginning when it formed after the Big Bang. So photons were very important. Photons, positrons, electrons were the cosmic plasma. We've talked about that in previous lives. The neutrinos were there as well, and neutrinos had a bit of a breakup with the cosmic plasma back then soon after the Big Bang because actually the expansion rate was a little bit faster than the rate at which the neutrinos were interacting with the cosmic plasma. So it's almost like the neutrinos were like, goodbye, let me break away a little bit now. So it's very interesting, even just studying Big Bang nucleosynthesis, if you see my live streams on that, would kind of tell you more about this type of thing. But baryons were very little part of the Big Bang nucleosynthesis, even back then, even at the beginning of the universe. And now we've gone from radiation dominated to matter dominated, where, by the way, matter is both dark matter and baryons. So it turns out that when you consider just the matter part of the critical density, you see that only 5% is ordinary matter and 25% is dark matter. So overall, around 30-ish% is matter. So then we thought, okay, maybe we went from radiation dominated to matter dominated, right? But actually, it changed again, and now we're more dark energy dominated. So it's dark energy 70% and matter 30%, where 25% of that is dark matter. So the most biggest contribution to the cosmic inventory is first dark energy, then dark matter, and then only 5% is baryons, which is what we're made of. So it's a very interesting thing. And also, I like to ask this as a quiz question on my lives. So now I said that we're made of baryons, but even then, the most type of baryon in the universe is just hydrogen. So hydrogen is the most abundant element. We on Earth might not feel that way because our atmosphere has, a lot of other things that were made in this environment. We're lucky because our atmosphere at one point was poisonous. It had a lot of carbon dioxide, just like Venus still does. But that's because Venus doesn't have liquid oceans of water, which could have absorbed the carbon dioxide like we did here on Earth. And then we kind of cleaned up our greenhouse effect basically by turning that carbon dioxide to rock in the form of limestone. So we're very lucky the way we experience things. And you might think oxygen and nitrogen are very important. It is to us, but in the overall universe, it's actually hydrogen that's the most abundant element even now. That's what the sun is doing, converting hydrogen to helium. Jupiter has a lot of hydrogen. So yeah, I just wanted to put in perspective that our experience and being Earth-like is turns out pretty special. We don't have evidence yet that there are other environments exactly like ours, and so what you might think is very important, and it is very important here on Earth, is it's a slightly different picture, quite a bit of a different picture in the overall universe. So I know it sounds kind of weird about the dark energy thing, but it is actually a very important question, so that's why I took a long time to answer. Absolutely. So we can talk about the supernova data in more detail too. I can see some more things coming up. So then somebody asked, is it true that we found water on Mars or something? If so, can we plant stuff there? Yes. So we do have evidence of water erosion on Mars. So there probably was liquid water in the past in Mars. So remember, even Earth. So Earth is very interesting. So you know how our moon, so we have a moon, we have one of the giant moons actually of the solar system. There are 7 giant moons in the solar system. We have one of them. We also just have one moon in general. But if you think about our moon, one of the biggest sort of notable features about it is the craters, right? Impact craters on the moon. So there was an era in our solar system in its 4.6 billion year evolution. There was an era, we call it the era of heavy bombardment, where these craters formed, basically. And we were hit by them too. We were hit by planetesimals to get these craters as well. But I'm saying this because I'm trying to say that Earth is a very active geological site. So because Earth gets volcanoes, we have volcanoes happening, which paves over the surface. So it makes the surface more new. New as in volcano will happen, the lava will come out, it will pave over the craters. So it changes the surface. So we might not see as many craters here on Earth because of that. Also, another thing that happens a lot on Earth, and you know this already because you've probably been to such places with such things happening, which is wind erosion and water erosion. Thank you for liking the live, by the way. Please do like the live. So, wind erosion and water erosion, you can put examples of that in the chat if you like. Some famous examples are here on in North America, for example. Those those types of things also are very telling for a planet because we haven't been on the planet for all the full 4.6 billion years, right? So we're kind of understanding about what happened on Earth by looking at the effects of erosion, like water and wind. So, for example, the Grand Canyon, we didn't necessarily see the Grand Canyon being formed, right? Like actively, like, I mean, it's still being, it's still changing. Like Antelope Canyon, I was there last year. Antelope Canyon, when it rains, it becomes like a washing machine. Like you would die there. You basically, if you're stuck down there, like it literally spins you around. It's actually really bad. Like, so don't go to Antelope Canyon when it's gonna be raining. So yeah, so there's that. But basically, all of these are evidences of erosion. So your question about water on Mars is that, thank you for liking the live, really appreciate it. Your question about water on Mars is that we have evidence of this erosion on Mars as well. We have evidence of water erosion. So we think there was water in the past, and then there's still what's still happening a little bit is the wind erosion. Now, Mars doesn't have a substantial atmosphere because of its lower gravitation, and it's also cooler on Mars. So, but yeah, there is Mars is pretty good of a choice, especially if you're okay with the cooler weather there. Venus is too hot, and also the atmosphere is poisonous. That's really the saddest thing about Venus, because Venus is more like Earth. Venus, the mass and size of Venus are more like Earth. So really, the more comfortable, very much like Earth would have been Venus, but it's very hot there, being closer to the sun, and because of the greenhouse effects, and because it has a ton of carbon dioxide in its atmosphere, and its temperature is it's like 740 Kelvin, if I remember right. So very hot. But Mars, being farther away, farther out at like 1.52 astronomical units or something like that distance from the sun, where we're at 1 astronomical units, Mars, if you're okay with the cold weather and cooler seasons, even the summer is going to be a lot cooler on Mars. It's not a bad place. And I don't know that exactly what we would do with the water situation now, because there's not, as far as I know, substantial water right now on Mars to really talk about, but there's probably something that can be figured out. Why won't you acknowledge the Star Wars galaxy? Star Wars galaxy, which one are you talking about? I'll acknowledge any galaxy if it's a galaxy I know about, for sure. So we've talked about the Milky Way galaxy. That's our galaxy. We've talked about our neighbor Andromeda galaxy. We actually talked about how the Milky Way and Andromeda will merge in 6 giga-years, in 6 billion years. And unfortunately, we might not be here at that time. And the sun, so by the way, this is cool too. We talked about how spiral galaxies, when they merge together with I guess Andromeda is a spiral galaxy, right? Am I saying that right? I think so. But anyway, when we merge, pretty sure Andromeda is another spiral galaxy. We should check that. Somebody check that, Google it. But basically, when they merge, they will make an elliptical galaxy. So it's a different kind of galaxy shape. And I wish we could have seen that. Thank you for liking the live, by the way. I wish we could have seen that. I would love to see our galaxy evolving, but I guess we might not be here at that time. Boss says it's a real galaxy. Okay, Valerie says, hello. Are you a scientist? I am. I am a physicist. I did physics, is my background. If speed of light can't be done, why has it been proven in the Star Wars universe? Maybe you're joking, but are you talking about the movie? If somebody says something in the movie, that doesn't make it a scientific fact. Thank you, though. Thank you for being on the live. Your data is outdated by the minute. Could dark matter and energy be related? Like, if we figure one of them out, could it explain the other? She works for Elon Musk. What? Anything made of mass cannot be faster than life. If you do time travel, you wouldn't be able to report back because time would be so forwarded. Hi, the real EEBKK. Adam is coming next. Hello. Hello, Crazy Sick Wine. Hello, the real. Hello, Robert. Robert says, thank you for answering my question. Of course. Sorry, it's taking me a little bit of time to get to everybody's question, but I wanted to spend time on the the relevant questions that are really important to talk about. If you ask about dark energy, of course, I'll spend some time on that because it's a very important topic. I was watching The Matrix. Hello, sirs. Hello, Crazy. Who is your favorite astronaut, if you have one, and why? Oh gosh. Maybe Kalpana Chawla, but I feel really bad because she died. Who is your favorite astronaut? That's a great question, actually. I should have a better, I should think about that more. But I think Kalpana Chawla. Do humidity have to be part of hat in fire, being of something on Mars? In UFO pass to sun fired of the sun? I'm not sure I get that hat. Thank you, James Woodlife. James said that he looks at my shorts. Thank you. Thank you, thank you, thank you. So now let me go back to somebody asked a question. I just wanted to make sure I see every comment. If I missed your comment, just please type it again. Thank you so much. Sorry about missing it. If I missed it. Their food is falling with the help of gravity. So I think Reese had a question. Could dark matter and dark energy be related? So that's a great question. It very well could be related. We think that they're sort of different things. So dark energy is sort of this, it's considered the energy of the vacuum, if you will, or this negative energy. Because if you think about it, when we consider gravitation, it makes things come together more, right? It's an attractive force. Basically, if you think about gravitational energy, when we even talked about gravitational potential energy release of Jupiter, where we were wondering, why does Jupiter release so much thermal energy? Jupiter actually releases a ton of energy. As a planet, it's kind of crazy. I mean, Jupiter is kind of crazy. Jupiter is an amazingly big planet. It's the biggest planet in our solar system. It has 300 times the mass of the Earth. And it outputs a lot of energy. And that energy is actually coming from most of it is coming from its contraction because it releases gravitational potential energy. So anyway, that's to sort of give you an idea for other types of energy. But as far as our experience, right, gravitation is a type of, attractive force that makes things collapse. Like a star will collapse under its gravity. And then it'll be, what's left behind at the end is some compact object. After it's done sort of exploding and dying, it'll leave behind either a white dwarf or a neutron star or a black hole. So gravitation makes things come closer or collapse, whereas dark energy is sort of this anti-gravity force, if you will, which is making things expand. It's sort of a negative energy in that sense that it's making things expand out. It's making the universe stretchy, you know. So it's kind of different in that sense. Dark matter, on the other hand, it's not necessarily. Also, another thing is, remember the history of dark energy is the cosmological constant. So, as old as Einstein's general relativity equations, this cosmological constant has been relevant. Now, we have shifted dark energy to be more general now. The cosmological constant is one case of the dark energy model, basically. But we know that even Einstein, even Newton had to deal with the fact that the universe is stable. In fact, we know now that it's expanding, but at that time they were wondering, like, okay, we know that a large scale force at play is gravitation. Einstein developed general relativity, which is an explanation. It's an updated explanation for gravitation, where it doesn't really treat gravitation as a force, but a fabric of space-time. It's a curvature. The space-time is curved with a massive body. So, but it is a theory for gravitation, right? It is a theory. It's a set of equations for gravitation. When we when we measured gravitational waves from a neutron star binary merger, that's a confirmation of Einstein's general theory of relativity. So basically, we knew as far back as over 100 years ago that there had to be something else going on in the universe that is sort of an anti-gravity. It opposes this collapsing type of thing at a large scale. So we know that in the scale of a star, for example, within a star, if you don't have enough nuclear reactions going on, the star will collapse upon itself. The only thing keeping the star from collapsing, because the star is a massive object, is the fact that it has a nuclear reactor at its core, and it's doing nuclear reactions, and it is burning nuclear power to keep itself as a star, and to keep itself alive. Even the sun is doing that, right? So a star is a star while it still has a nuclear reactor going in its core, and it can oppose gravity. So when you ask the same thing in terms of the universe, we were thinking, even Einstein, even Newton was confused about this, because everybody knew that gravitation plays a role at a large scale, but what is keeping things from collapsing? What is keeping things from the universe just collapsing upon itself? There had to be something. So Einstein introduced the cosmological constant in his equations to account for the fact that the universe was stable. Now, this was before Hubble did his observations, found more galaxies, and eventually we saw that the universe is not only stable as in it's not collapsing, but it's actually expanding. And then later in the 20th century, we even found that its expansion is not only happening, but it's accelerating. So that's where dark energy comes in. This phenomena of the expansion and this anti-gravity, this history of the physics evolving is dark energy. Thank you, Alex. I'm looking at the comments over there too on my laptop. So this cosmological phenomena, that's dark energy. Some people consider it almost like a, like you'll hear people talk about it as cosmological constant. They think of it as literally, like, maybe it's a property of the universe, you know. It's almost like this, like, it's almost like the universe does that. Like, maybe that's what it is, you know what I mean? Like, it's almost like an intrinsic property almost. Now, I'm not saying you have to be convinced by it, because it is still the case that dark energy is a mysterious topic, so we should try to understand it more. But dark energy is almost like this property. Dark matter, on the other hand, is somewhat different. It's they could be related. They could be related, but dark matter seems to be more of like this like weird invisible matter, like stuff that's there but we can't see it because it doesn't interact with light. And it very well could be a type of particle that we haven't discovered yet, you know. So there are dark matter candidates, and um, there are dark matter there are dark matter candidates, and we spoke about how neutrinos, WIMPs, and machos, those things are acronyms, were dark matter candidates. So we talked about neutrinos being a dark matter candidate because neutrinos also don't interact with photons. Or sorry, neutrinos also don't interact with electromagnetic force. So, you know, so we know of other particles that are also elusive. They're also real and they're also elusive. So, you know, maybe dark matter is a type of particle that we just haven't discovered yet because we are not necessarily sure that we have discovered everything there is to discover, even in a field like particle physics. In fact, we haven't, because there is this topic of dark matter that is also a mystery. So we talked about it, but basically we considered neutrinos could be the explanation for the invisible matter, because there is a lot of neutrinos being formed in different, pretty much every process as well. We did some math and we found that no, actually neutrinos don't really account for it enough. And then we considered weakly interacting massive particle with basically the inspiration that, well, neutrinos didn't do the job, but maybe we can dream up a different type of particle that has more mass that could kind of act like a neutrino, but maybe that's what dark matter is. So that's a WIMP. And then we talked about machos, which were basically massive compact halo objects. So dim objects in the halo of our galaxy where they don't really contribute much to the luminosity, which is exactly, you know, the issue with dark matter. Dark matter is dark. It's not bright. We didn't know it was there, but apparently it's there, type of thing, you know. So we considered these types of candidates, and so far we haven't really determined exactly what it is, and the search is still on for dark matter. But dark matter seems to be, it's not, I know it's confusing to say the sentence like this, but dark matter seems to be something substantial, something matter, like some stuff. It seems to be some stuff, whereas dark energy is more like this, almost like this property of the universe, if that makes any sense. So I just wanted to give you that view, which hopefully kind of helps to, you know, put things in alignment. But at the same time, let me just wrap this section up by saying that dark energy, lots of it, and we don't know exactly what it is, and dark matter, again, lots of it, and we don't know exactly what it is. And those are the correct order of stating those two things, because dark energy is 70% and dark matter is 25% of the universe's critical density. Okay. So it's always fun to talk about this particular topic, because I feel like it is so relevant. Until we solve these things, we can keep talking about it and learning about it without any reservations, because it's always time well spent, pretty much. She works for anything. Oh, I think I'm reading the comment again. I think it was anything made of mass cannot be faster than light. That's right. Exactly. If you do time, so that's a great point. So anything, only the photons are massless. So photons, which are massless particles of light, basically they make up light, do travel, of course, at the speed of light. So especially the speed of light in vacuum. So the speed of light in vacuum is a constant. Even though that sounds like a very trivial sentence, it is actually what completely changed our view and understanding of the world, of the universe, actually, and completely changed speed of light. Yes, completely changed how we understood electromagnetism, actually. So even though the electromagnetism equations were sort of, they were already there, the Maxwell equations, which give us an understanding of E&M, were pretty much there already. A lot of people, Faraday, Maxwell, you know, Gauss, like there were a lot of people who contributed to electromagnetism. And so a lot of this groundwork was already there. But when Einstein came in, and in the year 1905, he published on special theory of relativity, it basically gave us a groundbreaking kind of insight. So it's almost like you can have all these facts put on the table. Well, you might want to, he did a lot of literature search. So he also, kept in touch with all the physics, work that was coming out, all the developments, if you will. Like he was looking at all the findings, all the research that was being put out. And then it's almost like you can put everything on the table, but then there's this like deeper understanding of it that you can gain when you're someone like Einstein. And that's what he did with electromagnetism. He gave us this new, deeper, and just like this completely life-changing insight into electromagnetism with his special theory of relativity. So the fact that the speed of light is a constant in vacuum, it's a constant of nature. It's not just a trivial constant, it can be changed. No, it's a constant of nature. So he talks about when we read the that was weird. When we read the book on Einstein's journey with all this work, it's a book called Einstein's Cosmos by Michio Kaku. We actually covered that book here on the channel a while ago. When we read that, we saw that he was doing these thought experiments to imagine like basically racing with a beam of light, and he realized that even if your speed was very close to the speed of light, like say you're going at point, so say speed of light in vacuum is a constant of nature. So say that is c. Oftentimes in physics, we just call it c. Even if you're going at 0.9 c, you would still experience c to be the speed of light. So that actually changes everything, turns out, because from there we get the relative nature of space and time. So space and time, space-time, it's a four-dimensional, space-time. Basically, space-time has the three spatial dimensions and the one time dimension. So first of all, being comfortable with this four-dimensional type of understanding is good, because that's basically space-time. But the fact is that because of the speed of light being a constant of nature, space-time becomes relative. And there's length contraction and time dilation. And not only that, we also have mass and energy equivalence. E equals mc squared. All those, the famous equation comes from that. So that's where I think this comment, that's good. And I just wanted to tack on this particular piece, which is that the speed of light being a constant of nature in vacuum, and yes, other things with mass more than a mass of zero cannot have that speed. If you have doubt about this, and you are interested in the time travel and the space sci-fi type of stuff, you could special theory of relativity is the thing that you need to read about. It'll be really interesting and hopefully clarifies all of that. And also, we did talk about a wormhole example from the same book that I think it was Kip Thorne who came up with that. So it's not like that the topic of it's not that we didn't consider time travel at all on this channel. We do talk about it sometimes. I'm not into mass times Energy is equal to mass times E equals mc squared. Yes, 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 indeed. Thank you. Hello, Renee. Such a mesmerizing, you make me feel at peace. Awesome. The secret to originality is to hide your sources well. Oh, wow. Is that what he said? Let me go back down. But yeah, thank you for the comments about the speed of light. That prompted me to talk about special theory of relativity, which of course gives us the updated theory of electromagnetism. Granted that electromagnetism, of course, was contributed to greatly by some of the fathers of it, such as Michael Faraday and Maxwell and other people, Gauss and people like that. But bringing it all together and adding that extra insight on the electromagnetism theory is what Einstein is most famous for. He is famous for relativity. Now, he did not get the Nobel Prize for it because people were still kind of struggling to understand exactly what he came up with, but that's what he's actually famous for. So if you're ever interested, we actually do cover special theory of relativity as well in the past in our live streams back in the maybe like October or something like that. So we did cover that as well, and it's extremely relevant to the some of the light type of questions that I see here. Wait till they split atoms. Well, we already can split. Thank you. We already split nuclei. So is that what you mean? Did you? So we talked about the atomic bomb, not not my favorite topic, but some people's favorite topic is actually something to do with war. So it was also kind of popular actually when we talked about that. So we talked about nuclear fission and oh, thank you. Oh, Feynman, yeah. Feynman is great. Thank you for liking the live. Feynman is who gave us the Feynman diagrams for particle physics. So, pretty good guy, I would say. I met his sister, actually, at a conference. At a conference. Right? I think so. Yeah. I have to double check, but I think I met his sister at a she gave a talk. So yeah. It was actually right around a dark matter talk. So I think I was there for the dark matter talk and met her instead. She also gave a talk. Pretty good one. I think she said something like he was sort of a difficult brother. I don't know. It was he's probably an okay guy, I don't know. Hope you're so yeah, the question or the comment about splitting atoms, we already split. Very cool. Yeah, yeah. We already split nuclei, if that's what you were mentioning. We already did that. We did that. We made bombs out of that, and we dropped them too. Even though some of the people who worked on the nuclear fission science actually thought that we would only do like demo bombs and not drop them on actual people, but you know, that was history. That is history. Hope your day went well. Thank you for all you do. Thank you. Thank you for answering my question. Of course, thank you. Thank you, Robert. Thank you, Alex with pause. Wait. Do humidity have to be a part of that in fire, being of something on Mars. Oh, in UFO pass to sun fire out of the sun. So somebody I think asked about the humidity on Mars. I'll try to. Alex with pause asked, "What's your favorite planet, if you have one, and why?" I was waiting for somebody to ask. Thank you so much for asking that question. Thank you. I love it. I think it's Venus, actually. Like, it's Earth. You know, I love that we got Earth. You know, other than Earth, I think it's Venus. I think I really like. I'm sad that Venus does not and did not have oceans. I wish that it could have had oceans in some sort of way so that its atmosphere was more workable, and we could have gone to Venus, because Venus is also closer. So the other thing too is that Venus, let me tell you where Venus is. Venus is closer to us than Mars. So we could have gone to Venus more easier. And instead we have to make do with Mars because it's less poisonous. And I just think that's such a shame that Venus could not be. So let me tell you, the terrestrial planets are, of course, Mercury, Venus, Earth, and Mars. And these are the distances. So Mercury is at 0.39 astronomical units, pretty close to the sun. We found that the exoplanets that we keep finding are hot Jupiters and hot Neptunes. So real quick aside on that. And those were being found at like 0.1 astronomical units. So that this brings it full circle that how close those things are to the sun, to their sun. You know, our Mercury in our solar system, the Mercury, which we consider to be pretty close to the sun, is at 0.39 astronomical units. That's still more distance than 0.1 astronomical units. So really crazy, the exoplanet results that we've found. And then Venus is at 0.72 astronomical units, and the Earth is at 1 astronomical units. So, you know, Venus is right there, sort of closest to us. And Mars is at 1.52 astronomical units, like I was saying earlier. So Mars is not our closest companion, you know? So in some sense, I think my favorite planets are Earth and Venus, because poor Venus, it's the most brilliant object that can be seen in the Earth's night sky. Oh, and the phases of Venus, that's another thing, by the way, that we've also discussed on the channel. I don't know under which live stream. I go live like every day and I name them something. But no, of course not. Mars is not the closest. No. No. Mars is not the Venus is the closest. It's at 0.72 astronomical units. Venus would take a shorter time to get to. It's such a shame because I'm not a very patient person. If you ask me to go to Mars, you know, it's gonna take a while. I'd rather go to the moon or Venus before I go to Mars. But Venus, very very hot, very poisonous, unfortunate, very unfortunate indeed. Venus is easy to observe at its greatest elongation. So yeah, Venus, we talked about the phases of Venus. Did you know that the Venus phases are very the Venus phases are kind of different than our moon phases. So if you look at Venus really carefully with a telescope, you will see our beloved moon always helping us out. Our moon? Yes, of course. So you will see the phases of Venus if you look through a telescope, and actually how big I'll show you the picture in just a second here. We will show the phases of Venus, but you know how the moon, of course, also goes through phases from new moon to, full moon and crescent and all that stuff, gibbous and all that. Venus also has phases, and the phases of Venus are kind of special. They're kind of different from the phases of moon. And the phases of Venus, I believe, was also found by Galileo, and it was kind of a big deal. So Venus has been historically significant for our astronomy, and of course the brightest, most brilliant object in the sky. If you see the night sky, and you can't see a lot of stars, or what we say stars are really the bright objects. Most of the stars that you see in the sky, if you can see a lot of bright objects, those are actually galaxies. But the brightest object in the sky is Venus. Not the brightest star, but the brightest just period. Of course, other than the moon, if you don't consider the moon, with the exception of the sun and the moon, the next brightest object in the sky. Like even if you can't see a lot of other objects, you can probably see Venus. It's not going to flicker a lot, and it's going to be very brilliant. That's Venus. So I would say that's probably my other favorite. I'll tell you a little bit more. So when we observe Venus at visible wavelengths, because of course you can observe these things at different light wavelengths, all we can see is a nearly featureless white cloud deck. That's because of course Venus's atmosphere. So consider this, like if you're gonna be observing these planets, really it's not the rock or the rocky planets, that is. It's not going to be the surface right away if it has an atmosphere, right? So we actually see that atmosphere before we see anything else. So this nearly featureless white cloud deck, ground-based spectra, later supplemented by data from space probes to Venus, reveal that the clouds are made of sulfuric acid, H2SO4. So those are the clouds of Venus. They're not water vapor clouds. Cloud deck. I'm trying to find I think this is it. It's just basically we see the nearly featureless white clouds. Like it's just the clouds that we're seeing, and these clouds later on when we probe further, we know that they're made of sulfuric acid. So on Venus, if it rains, it's going to be the sulfuric acid rain. The sidereal, we get some acid rain here on Earth as well, but not as much. We're very lucky. We're very lucky that our rain is more nice. The sidereal rotation. So the most crazy thing about Venus is coming up next. The sidereal rotation period of Venus and its the sidereal rotation period and its orbital rotation period are very similar. So Venus is an extremely slow rotator. So it is the slowest rotator, just period, of all the planets, with a sidereal rotation period of 243 days. And the rotation is not only slow, it is also retrograde. That is, if we looked at the solar system from above the Earth's North Pole, we would see Venus orbiting in a counterclockwise direction, the same as the other planets. So around the sun. But its rotation is clockwise, which is crazy to me, Probably as a consequence of its slow rotation, Venus does not have a detectable magnetic field. So, if it's not going to rotate very fast, its magnetic field will be weak because of electromagnetism reasons. we can thank those people I mentioned earlier for that. Because the orbital angular momentum and the rotational angular momentum of Venus are in opposite directions, the sidereal orbital period and the solar day are related, and we know that the solar period is 117 days. So, very long time for it to be a solar day or a solar period. The surface temperature of Venus, oh, I was right, it's around 740 kelvins, hot enough to melt tin, lead, and zinc. Despite the long solar day on Venus, the surface temperature is nearly uniform over the entire planet, that's cool, I guess. This is because the circulation patterns in the thick atmosphere are highly effective at carrying hot air from the daytime side of Venus to the nighttime side, smoothing out the temperature differences. So because it has such a thick atmosphere, there's a lot of convection currents in that atmosphere, being very effective at carrying this hot air and smoothing everything out everywhere and making it a very homogeneous kind of temperature across the planet. The high temperature at the surface of Venus is a result of the greenhouse effect. The carbon dioxide stuff I mentioned earlier. The sulfuric acid clouds of Venus reflect about 75% of the light that strikes them. Below the clouds, however, the atmosphere is nearly transparent at visible wavelengths. So it's that sulfuric acid clouds is why we see Venus the way we see Venus, because remember, that's at the visible wavelength. So it's almost like whatever is going to reflect the sunlight off of Venus and also reach our eyeballs in the good wavelength where we can see it is what we see, right? That's where we think it's bright. So that is thanks to the sulfuric acid clouds, H2SO4 clouds, okay? Because the other stuff is pretty much below the sulfuric acid clouds, it is pretty much transparent at visible wavelengths. So we would not necessarily be seeing it as that white cloud thing. However, the energy absorbed by the planet's surface is re-radiated as infrared light, to which the atmosphere is opaque, thanks to its high CO2 content. So this is what happens when you get too many greenhouse gases in your atmosphere, something that we have to also think about on Earth here. The greenhouse effect is real. Look at what happens in Venus. It reflects the infrared light, but the atmosphere is opaque to that because carbon dioxide is in the atmosphere, which is opaque to that. And see what's going to happen here. The greenhouse effect on Venus keeps it that warm, which is like a self-fueling type of thing. It's never going to be cool enough to, oh yeah, somebody said 580 Fahrenheit. So thank you if you did the conversion from Kelvin to Fahrenheit, 740 Kelvin surface temperature. Thank you. Venus appears as a star. Venus is a bright object. So in astronomy, we just say bright objects. We don't have to classify something as a star if we don't know that it's a star. So not every bright object in the sky is a star, right? So I know we say stars, right? But the more correct way to call it would be bright objects or bright events. So if it's an event like a supernova, then we call it a bright event. If it's a bright object like a star or a planet or a galaxy, then we can just say bright object. Okay, hopefully that's helpful. I know some of the wordings are not that important, but it can help to clarify and remove the confusion, hopefully, okay? So now look at this, what happens. The energy absorbed by the planet's surface is re-radiated as infrared light, to which the atmosphere is opaque. Thanks to its high CO2 content, the surface air pressure on Venus is around 92 atmospheres, whereas our surface pressure is like 1 atmosphere here on Earth at sea level. So that same thing on Venus is 92. So like 90 times more. The composition of the atmosphere on Venus is 96.5% carbon dioxide and 3.5% molecular nitrogen. So, an intriguing question, this is my favorite part, is why the atmospheres of Venus and the Earth are so different from each other. Venus and Earth are nearly twins in radius and mass. Why then does Venus have nearly 100 times as much atmospheric pressure as the Earth? The key difference between the two planets, I've already said this, but I love it, in this context is that the Earth has liquid water covering most of its surface, our beloved oceans. Carbon dioxide dissolves in water where it forms, among other compounds, negatively charged bicarbonate ions. So we go from CO2, yes! We go from CO2 plus H2O to H plus HCO3 minus. Then this HCO3 minus is a negative ion, so it can readily combine with calcium ions, which are dissolved in the water. So Ca2 plus, because calcium will have 2 positive charges, Ca2 plus 2HCO3 minus is going to give CO2 plus H2O plus CaCO3. CaCO3, calcium carbonate, is poorly soluble in water, and so it's going to precipitate out of the water onto the ocean floor. Limestone, which occurs in abundance near the Earth's surface, is a sedimentary rock that consists largely of calcium carbonate. So because we're making limestone here on Earth, we're taking the carbon dioxide from the atmosphere and converting it. So since Venus is too hot for liquid water to exist, it lacks this mechanism for removing carbon dioxide from the atmosphere and locking it up inside the rocks. Like, we literally made rocks out of it, man. Amazing, just amazing. If you could somehow remove the carbon dioxide from the Venusian atmosphere, the remaining atmosphere, consistently mostly of nitrogen, would resemble the atmosphere of Earth prior to the emergence of photosynthesis. So on Earth, we did that. We made rocks out of carbon dioxide, and then we also gave birth to plant life, and then plant life also removes carbon dioxide and makes oxygen. So further cleaning of the atmosphere. So again, this is why greenhouse gases are very important to understand, and plants are very important to appreciate. Conversely, if you could unlock all the carbon dioxide presently contained in the Earth's limestone, the Earth's atmosphere would strongly resemble that of Venus. So we were more Venusian in our atmosphere as well, more like the Venusian atmosphere, but we cleaned it up. We had a way to do that. And then, to understand why we're so good with liquid water, there's the phase diagram for water we can talk about at some point. We already did in the past, which basically makes us such a good place for water. The Goldilocks effect. Venus is too hot for liquid water. Mars is too cold, but the Earth is just right. So that's the Goldilocks effect right there, and why we think of Earth as perfect, because it is, and hopefully will remain so. Thank you. I see the James Wood Life messages. Oh, nice. What is that? I see the velocity in the chat. Which one, which object were you talking about, Renee? Or maybe she left already. Alex says, gotta go by. Okay. Thank you everybody for joining. Can we get 30 likes? You are welcome. Thoughts on Richard Feynman? We talked about that. Ooh, thoughts on Neptune. That's a great question, Crazy. That's an amazing question. Thank you for liking the live. Thank you so much. Thank you for liking the live. Please do. Could we get 30 likes? Thoughts on Neptune. Ooh, I love that. We will talk about Neptune. I watched a teacher who taught Chinese to people who would warn viewers that she could. Hi, Kimmy. Thank you for joining. Renee says, yes, on traveling to Venus. Hi, Nathmi. Sorry if I missed some of your comments. I'm getting to everybody, I promise. Nathmi says, hello, Nathmi Dasanayake. Thank you for joining. Mars is not the closest. Nope. Our beloved moon always helping us out. Temperature melts. Lead. This whole existence baffles me. Venus appears as a star. Venus appears as the most brilliant object in the sky after the sun and the moon. Our beloved Earth, nothing compares and never will. Reese says limestone. Yes, very nice. Thank you so much, everybody, for liking the live. Really appreciate it. Could we get 30 likes? Can we? Sorry if I'm spitting. Can we? Can we get 30 likes? Yay. Yay. So Neptune, let's talk about Neptune. So. We know that the Jovian planets are Jupiter, Saturn, Uranus, and Neptune. And so we kind of club Jupiter and Saturn in a sort of a club, and we kind of club Uranus and Neptune in a different club. All of them are called Jovian planets or Jupiter-like planets because Jupiter is such an extraordinary, remarkable planet. We're kind of saying that the Jupiter onwards planets are sort of similar because they do have similarities. But Uranus and Neptune are definitely, a little bit different. They're still really big, but they're smaller by quite a bit. And they're, of course, a lot farther out. So we will look at the specific numbers, but Jupiter is at 5.2 astronomical units from the sun. So it's the closest Jovian planet from the sun. And it's sort of, the Jupiter Saturn are sort of in the middle of our solar system. So this is another very interesting fact. Thank you for liking the live, by the way. If we could get 30 likes, that would be amazing. We actually saw that when these planet systems form, or even the moon systems of Jupiter, Saturn, Uranus, Neptune form, the biggest satellites or the biggest stuff is sort of towards the middle of the system. So that is the case for our solar system as well, where Jupiter and Saturn are the biggest planets and they're sort of in the middle. And when you take the Jupiter system and its moons, we see that the biggest moon, Ganymede actually, is sort of towards the center. So interesting facts about, planetology there. But yeah, so Uranus and Neptune are quite a bit smaller, and they do not have, let me take a sip of water. Uranus and Neptune are sort of smaller. We will get into the specific numbers, but right off the bat, they do not have that metallic hydrogen layer that I talked about for the case of Jupiter and Saturn. So Jupiter has an enormous layer in its composition of metallic hydrogen, which is pretty crazy. Yay, thank you. Which is pretty crazy. Saturn has it too, but not as big. And then Uranus and Neptune don't have that. So the central pressures, so in other words, a bit of comparison here, the central pressures within Jupiter and Saturn are a lot bigger. The masses of Jupiter and Saturn, especially Jupiter, of course, is a lot bigger. So Uranus and Neptune are not as big, and they're much farther out. Okay? And I do believe we talked about a certain special moon of oh my gosh. We talked about a certain special moon of Neptune called Triton. So I know you guys probably heard of Europa, a famous moon of Jupiter. You've probably heard of Titan, a famous moon of Saturn. But have you heard of Triton? Triton. It's a famous moon of Neptune. And it is one of the giant moons. So let me read off the giant moons real quick so that I can keep mentioning them. So we have one of them. Earth has one of the giant moons. We just call it Moon, Moon. Then we have Jupiter's giant moons, Io, Europa, Ganymede, and Callisto. Then we have Saturn's giant moon, Titan. And then we have Neptune's giant moon, Triton. So Triton, I feel so bad also for Triton because, also, did you know that all of the Jovian planets actually have ring systems? The Saturn ones are super famous and remarkable, but they all kind of have ring systems. So Triton, in short, cutting to the chase here, is gonna become one of the rings, it turns out, probably of Neptune. Unfortunatamente, Triton is in a retrograde orbit, and that will affect its evolution such that it will basically the tidal forces on it will be such that it will basically eventually become one of the rings of Neptune. So let's read about that real quick. Then we can talk about it. So let me first say all the distances at which these things are, just for reference. It's the only moon that orbits in the opposite direction to its planet's rotation. Indeed. So the Jovian planets, Jupiter-like planets, these are, of course, Jupiter I mentioned at 5.2 astronomical units. Saturn is at 9.6 astronomical units. So sort of towards the middle of the system is Jupiter and Saturn. And then we have Uranus, which is at 19.2 astronomical units. So quite a bit farther out. And lastly, we have Neptune, which is what you asked about, which is at 30 astronomical units. So really quite far. And in order of decreasing mass, of course, we have Jupiter at 318, the mass of the Earth. We have Saturn, which is also big, but not nearly as big, at 95 times the mass of the Earth. Then we have Neptune at 17 times the mass of the Earth. and Uranus at 14.5 times the mass of the Earth. So Neptune is sort of the third biggest planet here, 17.1 times the mass of the Earth. So not the smallest of the Jovian planets, but not the biggest either, and really quite far. It's the farthest one because Pluto is considered, unfortunately for some, to be a dwarf planet, so not really considered a planet anymore. Okay, so since you asked about Neptune, which I think is a great question, good night, Reese. Thank you. Thank you for modding. Thank you so much. Meant a TV. Wow. Who needs TV when they can watch this channel on YouTube, right? Tell your TV person that they could just come for the astronomy live chat. Yay! Good morning. So, okay, let me read a little bit about Uranus and Neptune. So Uranus and Neptune are twin planets, similar in their properties. Uranus is 3% larger in radius than Neptune, but 15% smaller in mass. Their internal structure is quite similar with a layer of ordinary molecular hydrogen. So they do have hydrogen, but just as a molecular hydrogen form, lying atop a layer of liquid water and ammonia, which is called the ISIS in the jargon of planetary scientists, in turn lying atop a solid rocky core. So where Jupiter and Saturn have a substantial metallic hydrogen layer, Uranus and Neptune just have the rocky core. On top of that, they have the the icy layers, and then they have molecular hydrogen. Let me show you the picture. That will make it a little easier. Okay, so when we say ice in the context of the Jovian planets, we mean it could be water ice, or it could be ammonia ice, you know, some other material ice, if you will, as well. And I will show you the picture right now. But basically, yeah, internal structure, layer of ordinary molecular hydrogen, atop a layer of liquid water and ammonia, on top of a solid rocky core. And I'll show it to you right now. So this is Jupiter, this is Saturn, this is Uranus, and this is, wait a minute, am I saying it right? Yes, this is Uranus, and this is Neptune. And you can see how Jupiter and Saturn have an extra layer, that's the metallic hydrogen layer, whereas Uranus and Neptune just have the 3 layers. And if you can't see very well, I'll just tell you the layers. And the layers are just a rocky core, then layer of ice, and then on top of that, molecular hydrogen. So I'm still answering the question about Neptune, and along with it, I'm talking about Uranus as well. And Uranus, the planet, you know, so it's rocky core, on top of that ice, on top of that molecular hydrogen for Uranus and Neptune, okay? Whereas Jupiter and Saturn have the metallic hydrogen layer. Now we will further look at some more fun facts about Neptune because Crazy asked about it. So, yes. All the Jovian planets have a rocky core, actually. So if you saw that picture, you can rewind to it. All of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, have a rocky core. We say sometimes that it's almost like having an Earth-like planet at the core of these planets, screaming to be let out because there's so many other layers on top. So yeah, can you give me some advice? How do you know if a woman likes you? Okay, So, oh, here. So by the way, can we please like the live? That would be really awesome. Can we please like the live? So their internal structure, we just saw quite similar. And we saw what it was, the rocky core plus the ices plus the molecular hydrogen. Then, although the pressure at the base of the hydrogen layer is insufficient to compress hydrogen into its metallic form. So Uranus and Neptune are not as big or massive, right? So it does not have the very extreme environments of Jupiter and Saturn. So it's not enough pressure in there to turn hydrogen into its metallic form. So we don't have that metallic layer. The layer of liquid water is electrically conducting though, which is cool. And the rapid rotation of Uranus and Neptune produces significant magnetic fields. So even though it does not have the metallic hydrogen layer, but it does have the conducting water in it. Okay, so they're still really good. What do you call? Good at rotating fast and then having lots of magnetic fields. Okay. So let's see. I want to summarize a little bit, but this will help. Okay, I'll finish off with a little bit more fun facts on Neptune, because again you asked about it. So Uranus and Neptune, as mentioned, are similar in mass and radius. They're also similar in surface temperature. So we will see that they're kind of cold. So they both have a temperature estimated from their infrared radiation of around 59 kelvins. This is odd, given that Neptune's distance from the sun is 1.56 times the distance of Uranus from the sun. So this is actually really interesting because remember how Neptune is a lot farther away, right? It's a lot farther away. So this is odd because Neptune's distance from the sun is a lot farther away than Uranus's distance from the sun, which implies that Neptune intercepts only 40% as much solar power per square meter as Uranus. When the energy accounting is done in full, Uranus is found to radiate about as much energy as it absorbs in the form of sunlight. However, Neptune radiates roughly 2.5 times as much energy as it absorbs. This means that Neptune has an internal heat source. So yes, very interesting indeed, whereas Uranus does not. So these planets, again, we club them together sort of when we want to talk about them because they do have some similarities. But once again, they're kind of different. They're both similar in some aspects and different in other aspects. The reason why two very similar planets should differ so radically in their internal heating is not clear. So Neptune is really far. So we don't really know why it has so much more internal heating. It could be something like we saw with Jupiter, you know, the compression was leading to some more heat coming out of Jupiter. Remember when we talked about Jupiter? But it's very, very interesting. We don't quite know why this is the case. But let me tell you again, remember that Neptune is at 30 astronomical units, whereas Uranus is at 19.2. So it's another 10 astronomical units farther out than Uranus, but has a very similar temperature as Uranus, which is a little weird. So, and in mass, they're not too far off from each other. Uranus is smaller, it has 14.5, so Earth mass, 14.5 times the mass of Earth is the mass of Uranus. 17.1 times the mass of Earth is the mass of Neptune. But they have very similar temperature. So it's like what other sort of thing is happening within Neptune to make it generate more heat? That is a question. And it could have to be something to do with its contraction, maybe. Not sure. Hi, Mehrana. How are you? Where are you from? Well, I'm in North America. Where are you from? That's the continent. Sometimes I do continental welcomes. Ooh, can you like the live? Everybody, can you tap the screen and like the live, please? I was hoping to get over 30 likes and I only see 29. Thank you for liking the live. Really appreciate it. Thank you, very informative. Thank you. Welcome. So my continental welcome is Asia. Welcome. North America, South America. Welcome. Europe. Welcome. Antarctica. Welcome. Australia. Welcome. New Zealand. Welcome. Africa. Welcome. Yay. Thank you so much. Today has been really interesting, everybody. I feel like there were multiple really good questions, so it helped out a lot with this live to be more interesting and like a good discussion. So I'll keep going about Triton because Triton is the most interesting in a sense giant moon in our solar system. We just have the 7 giant moons. We have a lot of moons overall. I mean, just Jupiter alone, the Jovian planets have multiple moons each. Sometimes more new moons are getting discovered all the time. Jupiter has like 60 plus moons, and more are found every day almost. I don't know, actually. I don't know if they're found every day, but yeah, there's a lot. So, but out of the many, many moons in our solar system, there are just the 7 giant ones. And Triton is the one we're going to be focusing on for a minute here. So Triton, Triton, is very unusual because it's the only giant satellite that has a retrograde orbit. It's Neptune's giant moon, and it has this retrograde orbit, which you'll see in a moment will lead to its death. So Triton is a captured object rather than one that formed close to Neptune. The retrograde motion of Triton has important implications for its evolution, for the evolution of its orbit. As we saw, well, not here, but earlier, the Earth's tidal bulges act to increase the moon's orbital angular momentum. So the size of our moon's orbit is actually increasing with time. So thankfully, the moon has a bright future, pun intended. However, for a satellite on a retrograde orbit, the pull of the parent planet's tidal bulges acts to decrease the satellite's angular momentum. The size of a retrograde satellite's orbit decreases with time. So the current size of Triton's orbit in units of Neptune's radius is 5.9 times the radius of Neptune. So, but as a result of the shrinking of its orbit, Triton will move inside the Roche limit a few billion years from now. So again, this is in a billion years or so, a few billion years. Depending on its strength, Triton will either plunge intact into Neptune's atmosphere or be broken by the tidal forces into numerous fragments, forming a massive set of planetary rings. So depending on exactly how things will happen, it could either plunge into the atmosphere and just take a plunge and make its way into Neptune, or it could get fragmented and contribute to the various rings of the planet. So yeah, the rings are kind of like former moons of the planets, you know? It's like a former, yeah, former satellite almost. But not, doesn't have to be, but yeah, these planets are very much more extreme environments than our planet Earth. Very different types of things happen around them. Very different types of moons are part of their systems. And even within the same system, the moons can be quite diverse, actually, very much different from each other, even depending on their distance from the planet, as we saw actually with the Galilean moons of Jupiter. So we can talk about that another time, especially if someone asks. If someone in the live chat asks about it, then I'll definitely talk about it. But yeah, interesting facts about Neptune and Triton. By the way, if you're joining, can you please like the live? And if you missed our discussion, we talked about all kinds of interesting things. You can rewind and go to any other point in the live, I believe, if you drag the I think that's a thing, hopefully. Yay! I'm gonna get some more water. Let me know if anybody has any more questions. I know we talked about, I know I said I would talk about active galaxies, but I think I might do that tomorrow. Active galaxies will include a discussion, so let me just give a preview of that. We will talk about quasars. So we talked about galaxies in general, like more normal-ish galaxies. We talked about our own galaxy, the Milky Way, which is a substantial and quite large galaxy with a lot going on. And we talked about how the overall galaxy classification is something like spirals, ellipticals, and irregular galaxies. And sort of the differences too between these galaxies, and even within, say, something like a spiral galaxy, it has different components, and what sorts of things happen at what components is something of interest if you want to understand something like star formation. Star formation happens in more sort of these gas cloud, rich cloud parts of the arms usually. So we talked about all that. And then next we were going to talk about active galaxies, which is of course something kind of very different and interesting, and includes things like quasars. So types of active galaxies, we have Seyfert galaxies. I don't know if I'm saying the word right, but it's Seyfert, Seyfert galaxy maybe. Seyfert galaxies, that's how I'm saying it. Then we have quasars. Then we have, let's see, we have some radio galaxies we will look at. And then we will actually also talk about supermassive black holes and the accretion that they cause, and how from such accretion we can actually see them be rather bright, and that's actually how we can find these things quite more easily than one might think. Then we have quasars over cosmic history, so sort of a cosmic history lesson coming from quasars. And then we have probing the intergalactic medium, which is really interesting. Wow. And yeah, and then the next parts are clusters and super. We kind of talked about groups and clusters a little bit at, I think, my galaxies live. So some of this information we have covered in a different live, but we have not really talked about quasars yet. So it'll be very, very exciting to talk about quasars. I'll briefly mention what are even active galaxies, right? Active galaxies have many distinctive attributes that distinguish them from normal galaxies. So normally we've talked about, there's generally a supermassive black hole at the center of the galaxy. We talked about all the various different features. But one thing we will see with the active galaxies is that Active galaxies have much of their light concentrated in a small central region known as the active galactic nucleus, or an AGN. So some of you might have heard of AGNs, active galactic nuclei, and this is basically part of the active galaxies discussion. So that's one of the things. We will talk in much more detail about all the things that make up an active galaxy. And hopefully that will be helpful. And quasars are a part of that discussion. So yeah. There's a lot of emission, interesting emission discoveries about these quasars. So we will get into that. It's a little bit detailed, but it should be fun. Thank you so much for being in the live today. This is the book we're referencing. It is called Foundations of Astrophysics. It's a very common textbook that's used in a lot of astronomy and astrophysics courses. So hopefully you found it to be useful. Thank you for being here tonight. I support you 100%. Thank you for being in the live stream. Thank you so much. Thank you, Crazy Sick One. Thank you, Reese. Thank you, Mehrana. Thank you, everybody. Let me look at the live over here. Thank you, Fawcett. Thank you, Renee, Kimmy. I thought everybody was really supportive today, and now I'm gonna eat a Pocky stick. Thank you for your support, Crazy Sick One. Ben, see you tomorrow. Ben, I forgot to thank Ben. Ben is a regular. Ben, we will do more active galaxies tomorrow. Sorry about the... Do you like quasars, Ben? We will talk about it tomorrow. Thank you. Thank you, thank you, thank you. See you tomorrow. Is tomorrow Wednesday? It's snowing here. Is tomorrow Wednesday? I can't believe it. Tomorrow's Wednesday. I didn't go swimming today. I'll go tomorrow. Crazy, are you in California? Oh, I think I didn't know that. Maybe I missed that. I thought... Oh, that's right. You're in Florida for a vacation, but you're from California, right? good. Is it still bad in LA? I do look tired. I don't know who asked. I forget who asked about the expansion question. Oh, I think it was like a Robert. Lovely. I'm like, I want this Robert to come to the live every time and ask me that same question. It just like got me going. I love it. I love cosmology. Oh my god. Not as much, but I think I'm going to stay in Florida as long as I can. Yeah, man. East Coast, Beast Coast. Same coast, up and down. Hopefully no forest fires. Sorry about the forest fires in California. Cosmology is so interesting. I need to find more books in cosmology, or I'm going to write one myself. You know what I mean? I need to. I should find... You know what? Once this channel has more done, I will write more again. I miss writing, I think. Writing is very peaceful. Yeah, writing is peaceful. I think I want to be a writer again. I am a writer, but more. I think I will write again more. Writer and content creator. A hurricane? I hope not. How many more? It's too terrible. I'm so sorry about the hurricanes too, and the forest fires. I'm so sorry to Florida and California. And North Carolina. Some stuff happened there too. Terrible. Just terrible. Oh, I just want all the cats to be well. And the horses. Oh. And dogs and foxes. Oh. I do write, but I feel like my dream book to write is going to be a cosmology book. It is. I don't teach normally. Or no, I guess I used to teach. Yeah, you're right. Years ago. Years ago, I did teach a lot as a teaching assistant, but now I don't teach normally. Other than this, I did teach a lot. Kind of forgot. Yeah. But yeah, mainly doing this. Mainly this. Yay! Thank you, everybody. Yeah. I think some people are on the live. I'm looking at a very... Oh, did you have too much to drink last night? I have already forgotten what happened. Every live is a little cries. Cries? Cries. Live cries. Every live is a little crazy, is what I was gonna say, but I called it cries. Every live is a bit crazy. Today's live was amazingly... Today's live was amazingly on topic. Like, I'm blown away by today's live. If every live could be like this, that would be great. Positive vibes only. Excusez-moi. Today's live, guys, just amazing. Be like this. Ask physics, astronomy, and cosmology and astrophysics questions. It's so nice. I can talk about the topics. Also, Pocky, if you want to sponsor me, go ahead. I don't know if I like Pocky enough to accept them as a sponsor. But if you pay me, that would be great. There was a sponsor recently who said they would pay me and then they did not pay me. So I guess I showed their stuff just for free, which is fine if they had told me that, but they told me they would pay me. And then they didn't. Thank you for nothing. Pocky sticks, chocolate cream covered biscuit sticks. That was my dinner. Just kidding, that was my dessert. It's kind of cold, so I think I want to go to bed. Thank you, everybody, for being here. Really appreciate it. Really appreciate you. Good night, sleep tight. I want to go to bed, and then tomorrow I want to go swimming, and then I want to do some writing and posting and scheduling and work. And I want to, ooh, it's 222 on the microwave clock, which is a bit ahead. So I want to do all those types of things. And I want to thank everybody. Thank you so much. Ooh, if you liked the topics today, please do go find the other topics on my other live episodes. We cover a lot of these similar topics from physics, astronomy, astrophysics, astronomy, I said that again, cosmology on my live channel, live episodes. So find more on the under the live tab. Crazy, if you can share my live with any friends or relatives or distant cousins who might like this, I would much appreciate. Please do like, share, and subscribe, everybody. Thank you, thank you, thank you, thank you so much. Appreciate. Good night. Good night, good night, good night, good night, good night, good night. Good night, good night, good night. Ooh. I'm looking forward to the spring and the summer too, when the days are longer and I can go to the beach and then do my lives. Stay warm. That's right. Not as warm as Florida, huh? But we will most certainly try to stay warm. Ooh, and oh yeah, crazy. Did you know that I do my afternoon lives on the weekend? I'm going for a walk on the beach to look at our moon. You should try to see if you can see any craters. And remember that the dark spots on the moon are what are called the Maria. They were considered to be seas. They're not. They're just lowlands. The moon has highlands as well as lowlands. The highlands generally have the impact craters. The lowlands are the Maria. So enjoy the moon and its Maria. Try to find the Maria and the craters and enjoy one of the 7 giant moons of this solar system, which is our moon. Yay! Good night. Sleep tight. Have a good moon walk. Yay! Oh, maybe I'll leave you guys with Baji for a bit. Till we talk again, take care. Thank you. Let me show you Baji. Oh, look at this fur ball. Look at that. Mr. Baji Babu. Oh my God, Sachi Mama came running down. Sachi Mama, you were so sleepy. You almost tripped on yourself because you're so sleepy. And you're still running because she thought I'm gonna give her snacks. But did you get a lot of snacks already today? Yes, you did. Yes, you did. But still my mama came running. Oh, thank you. Thank you, universe, for my babies. Oh gosh. Good night, one. Good night, all. Thank you so much. Please do enjoy our topics, and please do keep on watching, and please do share and like and subscribe. Until next time, which is going to be tomorrow.